We'll continue from where we left off last time. So last time we stopped at these power calculations. We had nonlinear sources and then a linear load, right? So in that case, how would we calculate the power that is being transferred to the load? Nonlinear sources, a nonlinear source, and a linear load. How would we calculate the power transferred?
So calculate the current for each component of the voltage based on the different frequencies, and then calculate the power.
Sure. So every voltage component will have a corresponding current harmonic component because the load is linear. You give it a 50 hertz voltage, it will give you a 50 hertz current, right? Because of a linear load case. So, and then you add, so you have the voltage multiplied by the current multiplied by the cosine of the power factor, cosine of the voltage, the difference between the voltage angle and the current angle, which is the power factor. So VRMS IRMS cosine theta 1, VRMS IRMS cosine n theta 2, the nth harmonic, the angle between the voltage and current for the nth harmonic, second, third, fourth, and so on and so forth. You start with the average value if it has an average value. So the average value, average power for the DC for the DC case would be the average voltage times the average current, and the fundamental voltage times the fundamental current times cosine power factor. It's next harmonic, etc., so on and so forth. And then for the case of the sinusoidal source and nonlinear load, how would we do it? It's up there, but sinusoidal source and nonlinear load. In this case, I put across the load a sinusoidal voltage. The load is a nonlinear load. It will respond nonlinearly, so it will not necessarily give me. So if I put 50 hertz, it will not give me 50 hertz only. It may give me 50 hertz, maybe give me 50 hertz and 100 and 150 and 200 hertz current. So in that case, how would you calculate the power being transferred from the source to the load? The average power will only be generated by corresponding frequency. So if I have voltage that is 50 hertz, then only the 50 hertz component of the current will generate the average power. Everything else will be harmonics that is going to flow in the system because of the load, right? So the utility doesn't like that. The utility is producing this nice pure sinusoidal voltage here, V1 sine omega t plus theta, right? So this is a nice pure sinusoidal volt, single frequency. And then the load is responding by giving you some average current, and then first fundamental, second, third, fourth, fifth, all of these harmonics, right? What is actually producing useful average power? I don't have average voltage, so there's average current component is not producing anything. I don't have second or third or fourth harmonics of voltage, so all of these are not going to be producing anything. All of these harmonics are not going to be producing anything. All the VNs are going to be zero. The only thing that will produce the average power in this case is the fundamental voltage and the fundamental current. So all of this is going to be useless. And that's why the utility doesn't like harmonic content. So the utility will dictate the amount of distortion that is allowed in a system. And if you are causing the distortion, they will tell you to fix it. And there are power electronic ways to fix distortion. Right? So power electronics created the distortion, right? It's very weird. Power electronics created the distortion, and power electronics can fix the distortion. But it's extra cost. It's extra cost. So there are power electronic filters that can fix distortion, like a passive filter, but you can, program them to eliminate any number of harmonics, for example, using a certain technique. Yeah. We will discuss that later. So everybody's okay with this? The idea of sinusoidal, non-sinusoidal source and linear load, non-sinusoidal linear load, sinusoidal source, a linear source, or a sinusoidal source, and non-linear load. Right, so same thing for yes.
So if both are nonlinear, we have no common corresponding frequency.
No, you can have. I mean, if both are nonlinear, it's fine. You're free. Your voltage source is providing the fundamental third, fifth, seventh harmonic, applying that to a load that is responding also in a nonlinear fashion. What will it give? It will also give, fundamental second, third, fourth, fifth. Some of the components will correspond to some components in the voltage, and some components will not correspond. So something that looks like that actually is a brush, what is called a trapezoidal brushless DC motor. Trapezoidal brushless DC motor. It's also a, some permanent magnet machine. People call them, generalize and call them permanent magnet machine. So in these machines, when you were taking the electric machines course, you probably were discussing the fact that, torque generated by a machine is equal to some constant multiplied by the current, right? I'm sure you remember that if you took 338, right? This constant came from where? Probably it was called the back EMF constant. I don't know if Dr. Haytham maybe called it the back EMF constant or just said it's a constant and that's it. I'm not sure.
He said it was a
Construction constant. Construction meaning what? Construction meaning, in this case, it's actually a back EMF constant. So it's a back EMF constant that's due to the construction. Remember, we said that the back EMF is generated across a winding by this alternating flux that is so. So the number of turns you have in series, the winding pattern, etc., will dictate how much back EMF is seen across a motor's winding. So a motor's winding can be represented simply as an R, an L, and a back EMF source. So this is a DC, a variable DC source, for example, or a variable source, depending on speed. So this is a simple representation for a brushless DC trapezoidal, for a brushless DC machine. And this back EMF is actually what is generated due to the number of flux cutting the inductance, and because of the flux cutting the inductance, will generate this back EMF voltage. And the amount of flux cutting the inductance will depend on the voltage you apply, because the voltage you apply will change the current in the machine. So the current in the machine will change the flux. So this flux will change the back EMF voltage, right? So it's speed dependent, right? So these trapezoidal brushless machines, they actually generate a back EMF voltage that looks like this. It's not sinusoidal. So they are designed, the magnets in these machines are designed to create a back EMF voltage that looks like this, right? So if this is the back EMF voltage, which is directly proportional to this constant, okay? Directly proportional to this constant. So if I apply a current to this machine that is sinusoidal, I can do that. Because with a power electronics converter, I can control current to look like any shape I want. I can make current look DC, I can make current AC, I can make current trapezoid, I can make current triangular by certain modulation techniques that we will talk about later, maybe in chapter 7 or 8. Yeah. So if I apply a sinusoidal current to this machine, am I going to generate torque? Sinusoidal current at the same frequency. So this is, let's say, 50 hertz. I'll apply a sinusoidal current 50 hertz. Apply a sinusoidal current 50 hertz. Remember, the current times the back EMF constant, or which is proportional to the back EMF waveform, will generate torque. So I will generate torque for sure. So the fundamental, I'm only applying a 50 hertz current. And this trapezoidal waveform is also at the same frequency, at least the shape of this trapezoid is at the same frequency of this sinusoid. So it will have a significant component. If you do the Fourier series for this waveform, this red waveform, it will have a significant 50 hertz component. That will generate torque. And because of these, abrupt changes, it will have all these, and because of this flat section, it will have a set of other frequencies as well. So this set of other frequencies, are they going to generate torque for you? They're not. They're not going to generate torque. So that's why these machines, for example, when you drive them with a power electronics converter, you actually try to generate a trapezoidal current. You try to generate a trapezoidal shaped current. Because if you generate a trapezoidal shaped current, and the back EMF looks like a trapezoid, then every single harmonic of current and every single harmonic of the back EMF will create torque for you. But the motor will still run. It will still run, but it will just heat. It will not heat up in this case because you're not adding more current. You're adding current on. But how about if I do this? If I add trapezoidal current to a sinusoidal back EMF machine, this trapezoidal current has lots of harmonics that are going to flow in the machine, right? But the back EMF that's generated in the machine because of its construction is sinusoidal. So in this case, only the fundamental component of the current is useful to generate torque. But the current has so many other harmonics that are useless, that are just burning power in the machine. They're not generating torque. They're just burning power in the machine because of its current flowing in windings with resistance. right? So the way you generate current or you control current into a machine depends on the machine construction, right? So there are trapezoidal machines and there are sinusoidal machines. So, and power electronics is needed to do that. You cannot, I mean, how can you shape current? The only way you can shape current is, okay, current increased. I want to decrease it. How would you do that? Stop current flow. How can you stop current flow? With a power electronic device. So if I stop current flow for a little bit, then current will fall down. Or voltage that is being applied to the load that is causing that current, that voltage will fall down. If voltage decreases then, and you apply it to a load, then the current will decrease now. Right? And that's what power electronics does. So it controls, okay, the voltages that you apply to loads so that you can control the currents. Right? That's simplistically what we're doing. Okay, so same thing with average reactive power. So the average real power, we said, is generated by corresponding harmonics, and average reactive power is the same. So in this case, we said we have a linear source that's generating fundamental voltage, and we have a nonlinear load that's responding with many harmonics of current. None of these will contribute to reactive power transferred into the system. So none of these will contribute to the magnetic field in the motor, except the fundamental. None of these will contribute to the magnetic field in the transformer, except the fundamental, right? So we have to account for this other stuff, though, right? I mean, this is current flowing in the system, right? These are extra currents, harmonic currents flowing in the system. And we said that we rate our equipment based on what? How do you rate your transformer? We said, do we rate it only based on the amount of real power transferred, or average power transferred, or average reactive power? Apparent power. And apparent power has to include all harmonics, all the voltage and its harmonics, all the current and its harmonics. It's the multiplication of the VRMS, IRMS, total, VRMS fundamental, VRMS second, third, for all of these things. So this has so all of these harmonics, what are they going to do to my system components? They're flowing in the system and they're not producing the average or average real or reactive power that I need. That means that they're gonna be there and they will be additional to this other stuff that I need, right? So they will cause my apparent power to also increase, right? Obviously they will cause my system power rating of the equipment to increase. So we will have to account for them somehow, and we also have to account for them in the power factor calculation. So this is how they're accounted for. Power factor, we said, from the power triangle is the real power over the apparent power. That's from the power triangle that we came up with. And in the case where we have a linear source and nonlinear load, the real power is only produced by the fundamental voltage multiplied by the fundamental current multiplied by the power factor between the voltage and current for the fundamental. The apparent power is that fundamental voltage that the source is applying and all the current, the full RMS current, right? Because the current has a lot of harmonic components. In this case, that are due to the load, right? So we have to account for that. So how did this affect our power factor? The power factor for the case of a linear load was what? Power factor for the case of a linear load was just the cosine of the voltage of the angle between the voltage and current, right? So if you go back to our definition of power factor, it was cosine of the angle between voltage and current in the case of a linear load, right? But now, in the case of a nonlinear load that has this other stuff happening that is useless, has these other current harmonics flowing in the system that are not useful for me, the definition still is the same. The initial definition is the same. But when we apply the equations because of our nonlinear load being present, what happened was, fine, the V1 RMS goes away with the V1 RMS, and then I'm left with I1 over I1 RMS over I RMS. Is this a number greater than or less than 1? It's less than 1, right? So less than 1 means it will reduce my power factor. I want my power factor to be what? Ideally, I want to only transfer real power in the system. In that case, voltage and current, the difference between the voltage and current angles will be what? 0. So cosine 0 is 1. So ideally, I would like my power factor to be unity. Ideally, I would like it to do that. If I have harmonics in the system, can it be unity? It cannot be unity, right? So it's going to make my power factor, it's going to give me a poor power factor. You are charged for a poor power factor. As an industry, the utility actually gives you a guideline that tells you, okay, you cannot bring your power factor below 0.9. You're not allowed. or 0.95. I don't know what the guideline is here, and it will differ at different voltage levels actually. So at the distribution level, which is 240 volts or 480 volts, to be maybe a certain value. They would allow a certain amount of distortion. They would allow a certain value for power factor. At different voltage levels, at 132 kilovolts, they will allow maybe less, they give you a smaller margin for power factor reductions in power factor, and maybe less margin in voltage harmonic distortion. So depending on the level of voltage, they will give you margins for amount of distortion you can add in the system and power factor, right? So anytime you have harmonics in the system, it's clearly reducing your power factor. If it reduces your power factor, it means what? The utility actually charges you and you and you, and okay, it doesn't charge many people here because the employer is paying for the electricity or something. But the energy meters that you have in your house, they are only calculating real power. So that P, the average real power that's being consumed by your house. So if you have an air conditioner and you have a computer and you have all these other electronic equipment and fans and motors, fridge motors, all of this stuff, that is contributing to a poor power factor, right? If you have a poor power factor, what happens to your average power? Average power is what? IRMS times cosine the voltage, the angle between the voltage and current. So it's IRMS times the power factor. So if your power factor is 1, then the utility is charging you for the full amount that you're consuming. If your power factor is 0.5, they're only charging half. They're only charging half, and then because of the poor power factor, all of this current is flowing in the utilities cables to transfer power to you, but they're not being paid for it. Because it's harmonics, right? All of it's either harmonics or it's reactive power. And they don't charge for this or that. They don't charge residential consumers for this or that. Industrial consumers, they are able to control them better, right? They tell RasGas, no, you cannot do this. You have to maintain your power factor, worst case, 0.95. So RasGas has to comply. So if they have lots of components, if they have motors, lots of transformers in there that consume a lot of reactive power, that's something they have to consider. If they have lots of power electronic systems like drives, motor drives, for example, that are driving these big compressors, that these are producing these are nonlinear loads, and they will make your power factor poor as well, right? So then, okay, all of this stuff is your load. It contributed to poor power factor. You have to fix it, right? So one way to fix it is to add systems that will generate reactive power, like a capacitor. A capacitor will generate reactive power, like an inductor consumes reactive power, right? Inductive loads, they would consume reactive power, right? They would create this more inductive reactive power into the system. Capacitive loads will generate reactive power. So one solution would be to add some capacitors. How about if your system is fluctuating, if your amount of reactive power consumption is fluctuating, then at some point, if you add a lot of capacitance to bring the power factor very close to unity, and you now lose all this reactive power load, then what's going to happen to your power factor is it's going to go leading actually. And generators don't like leading power factor. Why? Because they reduce its capacity. In 459, we will talk more about that. Like if the generators in the power stations love, they would love unity power factor, which is not possible. It's not possible because anytime you have a cable with current, you have an inductance. So you definitely have a reactive system, an inductive system. But there are some loads that can be leading power factor, like capacitors, or having synchronous machines running in leading power factor mode, etc. So there are things that can have leading power factor. But if the overall power factor of the system is leading, the generators at the power system, at the utility will be affected. And again, that's a 459 topic, but just take it from there. So you always need to be lagging in power factor or unity at best. Okay, so this is what harmonics do. They reduce your power factor, right? So, and then how would you calculate this RMS current? As I said, it's like the voltage RMS calculation that we did before. You have to take every single component, square it, and put it under a square root. So the RMS value of the average value, RMS value of the first harmonic, second harmonic, third harmonic, etc. That's the RMS value of this non-sinusoidal current, right? It's a non-sinusoidal current waveform that you would calculate each harmonic component from the Fourier series, which I will give you the sheet for, and then you take all of these RMS components and calculate the full RMS value. Until when? You don't go until infinity, of course. I will tell you, for example, do the calculation until the fifth harmonic or something. Because beyond that, okay, what happens when you have Ohm's law? What does Ohm's law say? Ohm's law is V equals I times the impedance, right? If I would like to see what current is being put into the system, I will take the voltage divided by the impedance, right? The impedance for the first harmonic is one thing. The impedance for the second harmonic, remember, it's R plus J N omega L, for example. That will be the impedance, the dependence on frequency, because the inductance, the reactance will depend on frequency, right? So what happens if N increases? As we increase the harmonic order, what happens to the N? It increases. So what happens to the impedance? Increases as a value. So the voltage, so the impedance increases as a value. And then what happens if you looked at our Fourier series? Any of the Fourier series waveforms, as we increase the harmonic order, we are dividing by that, so the fundamental is cosine omega t. It's 4 Vm over pi cosine omega t. Third harmonic is cosine 3 omega t over pi, 3 omega t divided by 3. So as we increase the harmonic, we also divide it by a larger number, right? So what happens is, as your frequency increases, your impedance goes higher because of this. And your voltage goes lower because you're always dividing by this harmonic order. So for the 100th harmonic, you're taking that voltage and dividing it by 100, right? And you don't have a voltage waveform that is the 100th harmonic. The majority of it is actually the 50 hertz. You just maybe have some ripple on it that is causing some 100 hertz, 100th harmonic content in there. So the voltage content is small at that frequency. So the voltage content is small, and the impedance becomes larger at that frequency. So what happens to your current? At the higher harmonic components. Say it. It decreases, of course. If the voltage decreases and impedance increases, so this current harmonic at very high frequencies will decrease. Right? So that's why you don't need to calculate everything to the 100th harmonic. You will maybe do the first 5 components. And that will give you a close enough answer. For example. Okay. So this ratio of I1 over I, RMS, this that we found here, is called a distortion factor. Okay? So it's a distortion factor that we have to account for. So it can be, your power factor equation can be written as, the classical power factor equation, which is the angle, cosine of the angle between voltage and current, multiplied by the distortion factor that you have in your system. Right? There are other factors that are of interest to power systems people and power electronics people, like the form factor and the crest factor. So form factor will sort of give an indication of how close this waveform is to the average value, for example. And then crest factor is an indication of the peak versus the RMS value. Why would that be important? Crest factor is an indication of, it's a peak value. It's a peak value of a waveform over the RMS value of the waveform. Peak over RMS. Why is that important? Why is crest factor interesting here? I have a waveform like this. Right? It's producing a certain RMS, it has a certain RMS value. And there's a corresponding current like this, for example. Okay? So V times I, this will produce a certain amount of average power. Right? How about if the waveform looks like this? Right? This was my original waveform. But both waveforms, the area under both waveforms is the same. So if the area under both waveforms is the same, they will have the same RMS value, right? They will have the same RMS value. but one has a very high peak value, one has a very low peak value. Which do you think is better from a power system's perspective? You're building a system. You have to rate your current, your conductors, your switches and your power electronics devices and everything to what? To both. You have to consider the peak value of the equipment of the current that you have flowing in your system. And if you have a system if you have a fuse that is going to burn at, I don't know, 100 amps, right? You don't want to see this current. You prefer to see this current. If this current if it's producing the same power but with 10 amp peak, you don't want to put this with 100 amp peak because this will blow your fuse, right? So it's producing the same amount of power, but because of the distortion that we see in there, we have to rate our equipment to higher values. So it's more expensive equipment, right? So the utility doesn't like this. Yes, sir.
So the second waveform is it safe to say that the frequency components are way different as compared to the original?
Yeah, of course. I mean, this would be just a pure sinusoid fundamental wave. This will have a good amount of component at the same frequency as the sinusoid, at 50 hertz, for example, and it will have lots of other components because of these abrupt changes. It will have lots of other components. So it will cause the distortion factor. It decreases your power factor, but not just that. So it increases the equipment rating because of this power factor. So on an average perspective, it increases the equipment rating. Also, on a peak perspective, when you select your components, you also have to increase the equipment rating again because of this, because of the very bad shape, the crest factor. Okay. So this is just terminology. Okay, and then next slide is the same. Also, another very important, terminology. So it's called total harmonic distortion. So this is the fact that we have, if we look at the equation, what does this say? It's the total harmonic distortion is the square root of the sum of the RMSs of all the harmonic content except the fundamental. Right? So the sum of the harmonic content of everything in the waveform except the fundamental over the RMS value of the fundamental squared. So it's basically everything that you don't want to see over what you really want to produce, over what's really producing power for you, right? So ideally, you would like THD to be what? What would you love THD to be? As a percentage. We typically calculate it and multiply by 100 and give it as a percentage. Yeah, you would love it to be 0. You would love THD, total harmonic distortion. It's distortion, right? You want to have distortion to be 0. It makes sense from the terminology, right? But if you look at the equation, yes, I want everything except that's besides the fundamental to not be there. But it's there. You cannot have a pure sinusoidal waveform. There's no such thing as a pure sinusoid. So it will have some harmonic content, right? So how much is allowed? I mean, and then you can rewrite this equation. This THD can be written in, okay, you can calculate your RMS current, it's the full RMS current, subtract the fundamental, which means it's everything but the fundamental, divided by the fundamental RMS. So it's different ways to write it. And it's the same, it applies to voltage and current. So I can ask you for the THD of voltage or the THD of current. It's the same equation. Just remove I and put V. Okay? And typically, what the utility or the standards allow is 3 to 5% THD. They don't allow more than that. If you are going to do more than that, they will not give, your contract, you will be breaking your contract with them. The contract says you have to, your maximum THD in your system can be 3 to 5%. That's why power systems engineers, they will conduct a power system harmonic study of a plant. And one of the studies that you will conduct as a power systems engineer will be a harmonic study of the plant. You will look at all the polluting meaning electrically polluting, so these things that cause these harmonic content. So you look at all the power electronic devices and everything that has switching, right? It's either power electronics devices or switching. So if you have capacitors in your system, you're actually switching. If you have motors that you're turning on and off without a drive, you're actually turning them on or off with a switch. So this switching will cause abrupt changes. Anytime you have these abrupt changes, you will cause harmonic content, right? If these abrupt changes are, persistent, like you have a power electronic device now that's always there, like a UPS or a motor drive, these things are always there. So it's not like the ones that are there temporarily, like a motor starting case. So for a motor starting case, you have to deal with it differently maybe than with something that's persistent like a power electronic device that's consistently there, right? So they allow for a certain amount in your system. Yeah. And again, we said that this distortion factor will increase my RMS voltage and or current, right? Here in this case, we talked about pure sinusoidal voltage, so it was the current that was causing this trouble, and it's typically the case. So it will definitely have to contribute to the rating of your equipment, right? So this distortion factor that we calculated will increase your apparent power. So the apparent power will be VRMS times IRMS of the full system, which includes, so it will be the average real power, average reactive power, and then there's distortion component that we talked about, okay? Or and then here they will be called distortion volt amperes. It's the fundamental voltage multiplied by all the harmonic currents except the fundamental, right? So because P and Q here, this is assuming the case where typically the case is my utility is generating a nice sine wave. That's typically the case. Typically the case, the utility is always generating a nice sine wave because they keep their generators in top shape. It's the loads that are not controlled. So it's the loads that are responding by consuming these nonlinear currents. So typically you would have the real power would be V1 RMS, I1 RMS cosine power factor. Q would be the V1 RMS, IRMS sine the power factor, right? And then this D, the distortion factor, would be what? Would have to be the voltage, which is the only voltage you have is the fundamental voltage, the V1 RMS. And then you have to consider all the currents that are not the fundamental. So it's V1 RMS times all the currents, the RMS value of all the currents that are not the fundamental. Okay, so you've considered, it's a volt ampere, it's still a volt ampere measurement or value, but it accounts for everything that is happening in the system that is not the fundamental, not contributing to real power transfer. Okay? So that sums up chapter 2. The rest are some PSpice simulations. You will probably go through some of these simulations, calculation of power, etc., using PSpice in the lab and in your homework. So I'm not going to go through that. So we'll go ahead and start chapter 3, which is the half-wave rectifiers chapter. You've probably seen a lot of this before. You have seen a lot of this before. We will just formalize it in a more of a power electronic perspective and use some power electronics terminology, right? Maybe some of the stuff you haven't seen towards the end of the chapter, but most of the stuff you have seen. So, for example, a half-wave rectifier will be the basic form of a half-wave rectifier is the diode half-wave rectifier is you have a source, a sinusoidal source, and you have a diode here and a resistor. So what's this going to do? We look at the waveforms. So you have a sinusoidal source, a diode, and a resistor. If this is your input voltage, what will the output voltage look like? Yeah. So in the positive half cycle, this is my V input. The output voltage will look like what? In the positive half cycle, what will the output voltage look like? So in the positive half cycle, the source is producing a positive polarity here because of this positive value with respect to this point. So if this is positive and this is negative, and I have a resistive load here, it's a condition for positive current to flow. So if there's a condition for positive current to flow, then this diode will conduct. Right? So the diode conducts. If the diode conducts, this looks like this. The circuit looks like this. Right? It's a short circuit. It's an ideal device. So what does the output voltage look like in the positive half cycle? It looks like the input voltage, exactly like the input voltage, exactly the same. Right? This is V output. How about in the negative half cycle? In the negative half cycle, what would have happened if this diode was not there? If I apply a negative voltage here versus a positive voltage here, current will try to flow in the other direction. Is this a condition for positive current to flow? No, it's a condition for negative current to flow. So if you try to flow negative current through a diode, it will block. Right? So if the diode blocks, the circuit looks like this. It's an open circuit, and then I have my resistor like this. Right? So what does the output voltage look like? 0. Perfect. So how about current? No, current in the positive half cycle, assuming this is some R value, what will the shape of the current look like? Just the shape. What? What's that? Huh? Why is it a ramp? I have voltage across a resistor. Why will the current look like a ramp? V equals IR, right? So I is equal to V over R. So if V is a sinusoid, R is just a number, right? So the current will look exactly like the voltage, but scaled down with the resistor value, right? So it will be it will look exactly the same, but scaled down. And in a negative half cycle, of course, it will be zero, because the diode is blocking. So this will be your V, and the red waveform will be your I. Okay? So how about the voltage across the diode? V diode. What does the voltage across the diode look like? Come on, come on. Positive half cycle, what does it look like? Zero. It's zero. It's short circuit. I mean, it's a short, like when the device is on, it's ideal, right? It's an ideal device. So when positive half cycle, the device, the voltage across the diode is zero. How about negative half cycle? This is the voltage across the diode, right? What is it equal to? It's equal to the supply voltage, exactly. So it will look like the supply voltage. So if I'm designing this circuit, and this Vn has a maximum value of V maximum, what is the diode maximum voltage rating that I have to choose? I have to select a diode. I need to select the diode based on its maximum voltage rating. And in this case, the voltage across the diode is equal to the supply voltage. So it's Vm as well. So I have to choose a diode rated for Vm voltage. Okay? So what happens if I make it a little bit more complex, and instead of a resistor, I put a resistor and an inductor? Let me remove this case. So everybody's okay with this case? You're fine with this case? So now let me remove this case and put, instead of a resistor now, I put a resistor and an inductor. I have a source here, same diode, but I have a resistor and an inductor. And this is still my output voltage. When the device is on, the circuit looks like what? Like a source with a resistor and an inductor. And when the device is off, the circuit looks like this. When the device is off, right? Everybody agrees? It's either on or off, right? So, and that's why you will sometimes hear people referring to power electronics courses, for example, as, you know, switch mode power supply courses, right? These power electronics circuits operate in different modes. They switch modes between mode 1 and mode 2. This is a simple circuit that just had two modes, right? So some circuits have a lot more modes, right? So it's depending on the complexity of the circuit, you will have more modes of operation. But this is where the switch mode comes from. Yeah. Okay, so if the device is on, it will look like this. If the device is off, it will look like this. We all agree. So if the device is on, current will flow. If the device is off, current will not flow. Now let's look at the waveforms. So you still have your same input voltage here. Okay, so what does my output voltage look like? So positive half cycle, this is VO, positive half cycle. So in the positive half cycle, this diode is, if the voltage polarity is such that this is more positive than this, and I have an RL circuit connected here, then there's a condition for the positive current to flow, so the diode will turn on, right? So if the diode turns on, I have this circuit, this mode. So what does the output voltage look like in this mode? What? Same as the input voltage, exact same as the input voltage. The output voltage will look exactly the same as the input voltage, until here, for example. Is that the case? But what happens here? Huh? It goes off. Why does it go off?
It doesn't go off.
Remember, the diode will only turn off if there is a condition to force current to flow in the other direction. Okay. So now, what's happening to the current? Let's draw the current waveform. The corresponding current waveform. You have an RL circuit now. You have an AC source placed across an RL circuit. What will the current look like? Will it look like the resistor? In the resistor case, the current looked like this. Exactly like this, right? So as soon as you had voltage, you had current. As soon as you had voltage, you had current, and it looks exactly the same, just scaled down. You know, I equals V over R, right? And then at this point, current tried to flip directions, so you turned off the diode. Now we have an RL. So what happens when you have an L load? Exactly. So the current is what? Remember, the current through an inductor is an integration of the voltage, right? It was 1 over inductance, integration of the voltage over the inductance, right? So there's this delayed response, right? So if you put a voltage on this RL circuit, you will not see a current scaled down, look exactly like the voltage, but just a scaled down version. There will be a delay because, again, current rises through the inductor because of this equation. Because of the physics of the inductor, current will rise. It will take time for the current to rise through the inductor, right? So there will be a delay. It looks like this, and then the rise will be of an exponential shape because of the RL circuit and the first order differential equation, right? So it will rise exponentially, and then what happens? Where is it going to fall? For the resistor, the current went to 0 here. Why? Why did it go to 0 here? Because the voltage was 0. So because the voltage became 0, and then current to resistor is equal to V over R. So it's exactly the same, but scaled down. So this went to 0, this will go to 0, right? How about in an inductor case? We said that the current will always be delayed, right? It always be delayed. So if you have voltage the voltage across this, across this output circuit, across this RL circuit, the voltage went down to 0. Is the current going to fall down to 0? It will not. It will not fall down to 0 because, again, because of the inductance effect, there is a delay in current falling down to 0 versus the resistor case. Okay, they always draw the resistor case first and then see what happens next. So because of the fact that the inductor current takes time to rise and takes time to fall, then this current will not fall here, it will fall somewhere else. Maybe here, maybe here, maybe here, maybe here, maybe here, maybe here, depending on what? Depending on how big my inductance is, right? It's 1 over L, right? If this L is huge, if this L is huge, then it's going to take a lot for this integration to change the current, right? I mean, there has to be a significant value for this integration to change the current because I'm dividing by a big number, right? So it's a big number that I'm dividing. So if the inductor is large, this will fall back here. Or maybe actually, if the inductance is infinite, it will be continuous. It will never fall back again. It will rise and then stay. If it's infinite, of course, there's no such thing as an infinite inductance, but it's a case that we discuss in power electronics, right? It's a case we discuss. So if for a certain value of inductance, definitely the current will fall beyond where the resistor current would have become 0. Beyond with how much will depend on the RL values. We will look at the equations next, okay? But it will depend. Does everybody agree that it will fall beyond the resistor value? How far beyond? It will depend on the RL value. RL, the time constant, yes.
Right. So what you're saying is current will flow after the switch is on.
No, I didn't say that. Did I say that? I said current will flow after this point. So if current is flowing, can the switch be off? It cannot be off. So when will the switch turn off? Because what's happening here? Again, is this a linear circuit or a nonlinear circuit? This RL. Linear or nonlinear? No, nonlinear means, there are abrupt changes, or, if you give it a, if you give it a 50 hertz signal, it will give you a 100 and a 100 and a 150 and a 200 hertz component. This is an RL circuit, right? If you give it a 50 hertz component, it will respond with a 50 hertz component. Right? You remember in your 214 course, how were you calculating the current in this circuit? It was V maximum sine omega t divided by the impedance. Right? The impedance divided by the impedance. Was the frequency changing? V maximum sine omega t divided by the impedance. The impedance was a value. Right? The frequency does not change. Right? So the frequency is not changing, but the value of current will change. Right? So this shape will change. Yes, I agree. Because of the value, because of the fact that you have a certain voltage waveform, a certain current waveform. But the frequency of this component will not change. So what was going to happen to this current if I didn't have a diode? If I didn't have a diode here, I just put this RL circuit across this source. What was going to happen to the current here? No, if I didn't have a diode, I just put a source across an RL circuit. I put an AC source across an RL circuit. Yeah, it will go negative. Right? So if it tries to go negative when I have a diode, what happens to the diode? If you try to push negative current through a diode, it will turn off. Right? So as soon as you reach this point, the current was trying to go negative. It was trying to go, as soon as it tried to, okay, it will turn off the diode. Then the circuit switches into this mode. So now what does the output voltage look like? The switch is now on until here. Right? We agree that the diode was still on until here. So what does the output voltage really look like? What does V output look like? Guys, come on. Is it this blue waveform and stop here? Originally we said it was this blue waveform. And this is right. For this portion, it is correct. Exactly. It will continue for a bit. Until when? Until this point. And then it will do this. The diode turns off the circuit. Right? So this will be the output voltage. Right? So what happened to this versus the diode case? I added some negative portion, right? Is this good or bad? It depends on what output voltage you're looking at. If you're looking to create a high RMS value, then you've removed some negative portion. This is a negative area. It's going to remove from the RMS value, right? So good or bad depends on what your specs are, what you want to look at. Yeah. How about if I ask you to draw the waveform across the inductor and the waveform across the diode? Quick quiz. You do that and hand it in. Quick. I mean, it should not be too difficult. Yeah. Quick. Just your name. I mean, we want 5 minutes. I don't want more than 5 minutes, please. Think of the current waveform, okay? Think of the current. When you draw the inductor voltage, think of the current, because this current is actually flowing in the inductor, right? And VL is equal to L di by dt. Right? So think of this current waveform here.
Then I want VL.
Draw VL and V diode. I mean, V diode should be easy, but VL should be the one where you have to think a bit more. So VL is this, the current is this waveform here. This is I. Also do, you can, just to help you a bit more, right? This is V input, right? And this is current flowing, so this is VR, and this is VL, right? So V input is equal to VR plus VL. You know the shape of VR and you know the shape of V input, right? Because VR looks like what? Like what? No, no, not in here. What does VR look like? Actually, instead of drawing V diode, just draw VL and VR. Yeah, just draw these three. Yeah, just draw these. Should help you. I mean, come on. You have V input and you have VR. What does VR look like? Look like? How does it look like? But if it's, of course, the difference between the input voltage and inductor voltage. I agree. But you don't know what the inductor voltage looks like. So, but you know what VR looks like.
You could figure out what VL is.
What? This is the equation. You have V input only right now. If you don't know VR, then you don't know two things.
No, like VL can be found using the formula L times di over dt, right?
Yes, but you have I. So you have I as a shape. But what does this shape also look like? This is the current flowing in the circuit, guys.
VR looks like this shape.
Exactly. VR looks exactly like this shape of the current. Right? It looks exactly the same. So VR looks exactly like this, but scaled to some value. So you have now V input and you have VR. So draw VL.
You're saying that it doesn't backfeed into it can't dissipate into the battery, correct? Or your voltage source?
No, because as soon as the current tries to flip, the diode blocks. That's it. You cannot do that. I mean, it will not go back to the supply. You don't have negative current. Done? It's 2 more minutes. I'll collect the papers and then we'll continue. Again, it doesn't have to be exact. There are just certain points in the waveform. Just take 2, 3 points and then I mean, you cannot come up with the exact shape. Yeah. If you want to draw VD, draw VD. If you finished VL, extra credit. Okay, I'll select the picture again. Okay, so let's see what's happening here. So we said VL is V input minus VR, right? So at the beginning, V input and VR are the same, right? So it's 0. Agree? And then how about at the end? V input is a negative number, VR is 0. So it's going to be a negative number. So it'll be a negative number here. And then what else? So at some point, V input, again, this is the current, right? This is I. And so the VR is a scaled version of this, right? So maybe it goes up or down, right? Up or down, or maybe exactly the same, right? So at some point, V input minus VR is going to be 0. Where's that going to happen? Here, where? Think of the equation of the voltage across the inductor, right? 0. These two will be the difference between 0, meaning this VL L equal LDI by T equals 0. When will VL, which is equal to LDI by T, equal to 0? When this is not going to equal. Exactly, when the slope, when the di by dt, because again the inductor cannot equal 0. So when the di by dt equals 0, when the slope of this waveform is 0, there will be a 0 here, right? So, and between here, again I don't know the shape. In between these 2 points, V input is a high number, VR is a little bit smaller. I know that, so it's going to be positive. And between here and here, this is we said that this point is where they equal each other. So beyond that, VR is actually going to be greater than V input, so it's going to be negative. So it will look maybe something like this. And then there is no current anymore flowing in the circuit, so there's no change in current anymore, so also goes to 0. Yes?
If you're using VL is equal to L times di over dt,
Yeah.
isn't the slope at time 0?
Positive slope, positive slope, positive
Yeah,
slope.
so doesn't that mean VL should start from positive value and non-zero?
What?
VL should be your positive value, right?
Why?
Because there is a slope at that point.
No, the slope is actually 0 at the
Oh,
beginning.
really?
Remember, current is the integration of the voltage,
Right.
right? So what is the initial value of current? 0. So you started with 0, and then you built up current. Because of the integration, huh?
Slope is different.
I didn't draw it very nicely, but I mean that's why this I drew it a bit sharper than this. This I drew, sort of a flat here. This I drew, sharper. Because yes, as soon as the current starts to rise, you will have a slope, sure. A positive slope. I agree with that, yeah. Okay? So until where the slope becomes 0, you were all positive. After that, it became negative, right? So now what? Then VD. So everybody's okay with this now? Fine with this? Now VD. How do I draw VD?
It's gonna be a lot like your VL.
Is it like VL, or is it? I mean, until okay, VD until during when the device is on, it's 0, right? So it's 0 all the way until where? Till here. The device was on all the way until here, right? This is all 0. And then what? And then it looks like hint hint. Look like
Yeah.
exactly. Right here, it's open circuit, guys. This is an open circuit, so there's no current flowing. So then this terminal is basically this voltage, and this terminal is basically this voltage. Right? So then, you draw your input voltage maybe dotted like that, and this will be the diode voltage, the voltage across the diode. Okay? See, you've seen the simple circuit before, right? But drawing these waveforms, it will make you, it will make you appreciate what an inductor is. Right? Now you appreciate, wow, inductors, that's what they
I
do.
appreciate PSpice.
So, but yeah, that's good. So go and simulate this on PSpice, right? That's what you need to do. So now let's make it more complex, right? So we did just the R circuit and then an RL circuit. Then how about we do this? No, that's too complex. I said this course, I will only do first order systems. I don't have any second order. It's way beyond my mathematical capabilities. No. I will never take a big jump. Don't worry about that. So, but how about if I add a source? So let's say I put but I will simplify it first. I'll put an R. How about I put an R and a DC source? This is a VDC, and this is V input, and this is your diode. So this is just a resistor, right? We finished half the chapter, by the way, doing this stuff. That's it, really. Well, we'll just add a few equations next class. But for now, I mean, as long as you understand the waveforms, that's what matters. For power electronics, really, it's all waveforms. The equations, you will have them in the equation sheet, and we will go through them, and you will solve homework, so it's not going to be a big difference. So this is my input voltage, same thing. My input voltage is a nice, beautiful sine wave. This is my input voltage. And now we do the same stuff, okay? So this is my V output, okay? What does my V output look like?
You have a starting value for VDC.
Yeah, let me just draw a VDC here. This is my VDC and this is my V input. So what does my output voltage look like?
And start at VDC.
Exactly. So it will start here, and it will end where? Also here, right? It's the voltage across the resistor when the device is on is V input minus VDC, right? So when the device is on, the circuit looks like this. So VR is here is equal to V input minus VDC. Right? So if if VR is V input, if as soon as they're the same, then the voltage across the resistor is 0, so the current becomes 0. So what does the output current look like in this circuit now? Actually, let's do output voltage. The output voltage looks like it will start here and look like what?
Scaled down version of the
Scaled down version of V in. Is it gonna be a scaled down version?
Scaled up.
No. Basically, what it will be is basically I'm taking this line and bringing it down. Think of it.
Just P, right? Like
Hmm?
it's the VI minus VC.
So the V output is VDC plus VR. Let's draw the current first. Let's draw the current. Let's draw the current first. It will be easier. Yeah. So how does the current look like? Current I output. What does the current look like? Is the current flowing here? There will be no current flowing here because VDC is greater than the input source. There's no condition for the current to flow, positive current to flow. So V current is 0 here. How about now? What will the current look like? The current will look like V input minus VDC over R. So it's exactly this shape, but scaled, right? So I took this shape, my input shape. I removed the DC value from it, so I brought this whole thing down to my 0 line, right? So I took this V input and I removed from it VDC. So I moved this down, right? That's exactly what I did. And then I scaled it, right? So it looks like this, correct? And then it's 0. Everybody agrees? So if this is my current, what does my output voltage look like? What does my output voltage look like? The output? When the current is 0, so the circuit is open, right? So when the current is 0, it means my diode is still not conducting. This is my circuit. Draw your circuit and it will become easier, right? So this is my V output now, right? So if the current is 0, there's no current flowing, means the switch is off, the diode is off. So what does my output voltage look like? VDC, right? This is my output voltage here. If you measure across this, the output voltage will look like VDC, right? And then there's current flowing, right? When current is flowing, the output voltage is equal to what? It's equal to VDC plus VR. VR looks like this, right? Because VR looks like the current flowing through it, right? Exactly, it's just scaled. So it looks like this, and then current again is 0. So my output voltage is VDC. Okay? Okay with this? Now let's add a trick. Remember, this is now for the resistive case. What did we always say about the inductive case? You know, current will always lag where the case of the resistor, where the current stops for the resistor, the current will lag. And the rise will be from where the current was rising for the resistor case, but it will be a slower exponential rise, right? That makes it a lot easier now. So now I won't erase these waveforms. I will just add a nice little inductor here, right? So now my V output is equal to VDC plus VR plus VL, right? So now let's see what the current looks like. The current. Do we agree that until here, until this point, there's no condition for the diode to start conducting, right? Same thing. Same as before, the VDC is greater than V input. So if I put any circuit in there, there's no condition for the forward current to flow. It's only backward current. So the current will not conduct in this zone, right? So it's still also, let me redraw here on a different one. That's 0. Okay, and then what? Exactly, it will rise from where the resistor current would have risen, because that's the condition for the circuit to start conducting. It will rise here exponentially. I agree. In the resistor case, the current fell here. How about for the inductor case? It will be delayed. By how much? Depends on the value of R and L and VDC, right? So it can fall here, or it can fall here, or it can fall here, right? Depending on the value of the inductance that I have in my circuit. Okay? Simple, right? You draw the resistor case, extend for the inductor. Then it will be easy. You can easily figure out the rest of the waveform. So now let's choose one of these. Just draw one. So let's assume that this is my current waveform now, and it will fall, let's say, here, just for fun. Okay? Let's say this is now my current waveform. So if this is my current waveform, what does my output voltage waveform look like? So this was my output voltage waveform initially, with a resistor case. So initially, is it the same or not? Because there's no current flowing. And then there is current flowing in my circuit. That means the diode is on. So what does my output voltage look like? This is the circuit on condition. What does the output voltage look like? Just like this. Right? Just like Vin, actually. Just like Vin. Just like Vin. And then for the resistor case, it stopped here because current stopped here, and then it became VDC. For the RL case, where will it stop? Yeah, it will continue to look like exactly like Vn. This is Vn, right? This is my Vn, right? It will look exactly like, it will follow Vn all the way until the current becomes 0. So it's either here or here or here, depending on the value of inductance. And then current becomes 0, shoots back up, and becomes VDC again. Okay? We're okay with this? Okay. So we finished 3/4 of the chapter. So yeah, we'll see now. Okay, so we finished. I'll go through this, which slides we finished quickly. So we finished this, except for the equations. We'll go through the equations, but we finished all of this, all of these waveforms, all of this. This is the case with a RL and a source that we just did. So there's a case where they have just an L and a source case. I will skip that. That's not realistic. It's not useful, actually. So just this L and a source, it's fictitious, right? There's no piece of wire that doesn't have a resistance, right? So it's not a very useful case. It does not exist. We will not be using it yet. So yeah, so we'll stop here now. We finished, and basically we've covered, about half the chapter. Waveforms, okay? So next class, I'll go through, these circuits again that we went through. I'll just go through some of their equations. But at the end of the day, they're equations that you've seen before, like for the RL load case, for example, right? This is to come up with the equations for the current. The current looked like this, exponentially rising and falling waveform. It's an RL circuit that has a source, as well as you have to consider maybe energy that was stored in the inductor. So if you write the differential equation, this differential equation, if you'd like to solve for current, it will have, if you remember, forced response and natural response from 214. The forced response of the circuit was due to what? Superposition, right? So the forced response of the current was due to the fact that you had a source. Source divided by the impedance will produce a current that's equal to the voltage divided by the impedance. And then a natural response that's giving this shape, right? That natural response that's giving this exponentially rising and falling shape is the solution to the first order differential equation, where this source is equal to 0, Ri of t plus Ldi by dt equals 0. So it's a first order equation equal to 0. The solution to that is always Ae to the minus t over tau. How do you find A? We will talk about it. It's from initial conditions. So we will stop here. Next time we'll continue.